We've talked a lot about sine and cosine, and we've talked a lot about the unit circle and right triangles, but now we kind of want to bring all that information together and start talking about the graphs of sine and cosine. So to get started, let's go ahead and look at the graph of sine. So in order to talk about the graph of sine, what we're going to do is we're going to call it sine of x. So y equals sine of x. Because we're used to plotting points. For instance, plugging in something with x, getting out something with y. Now we're going to be working in radians. Now, if you're using your calculator to help you graph, that's great. Make sure you're in radian mode. Keep in mind that on exams you'll be doing a lot of graphing by hand, so you need to make sure you know how to use your calculator and also how to do these types of problems by hand. So if we were to graph the sine function, what we would want to do is we'd want to come up with some ordered pairs to graph. So a lot of times we would use a table to help us find those ordered pairs. A good idea is probably to start at the origin. Look at some standard angles as we move around the unit circle. And we can't just choose things from quadrant 1, because if we just chose things from quadrant 1, then we wouldn't see what's going on for the entire graph. Now we know when we get to 2 pi it starts to repeat itself. So I'm going to look at pi over 2 here, 5 pi over 6. We could look at 7 pi over 6. We could look at other numbers as well. 3 pi over 2. 11 pi over 6, and 2 pi. Then what happens at 2 pi is it starts going around again, and so I'll get all the same values. And this is called, for the sine wave to be periodic, meaning it repeats itself in a consistent pattern over a consistent time. So to find out what the value is when I plug x equals 0, the sine of 0 is 0. So this creates the ordered pair 0, 0. The sine of pi over 6 is 1/2. That's why I chose pi over 6, because if I would have chosen pi over 4, I would have had square root of 2 over 2 and needed to find a decimal approximation. The sine of pi over 2, and again these are ones that we have memorized, is 1. The sine of 5 pi over 6 would be, in the second quadrant, would be a positive 1/2. The sine of 7 pi over 6 would be in quadrant 3, so it would be a negative 1/2. The sine of 3 pi over 2 is a negative 1. The sine of 11 pi over 6 is in the fourth quadrant, so it would be a negative 1/2. And the sine of 2 pi brings us back to 0 and would repeat. So this is an example of pulling values from a table. Now I could have used negative angles as well. I could have had negative pi over 6, negative pi over 2, etc. I just chose the ones that were easier. Now as it turns out, when I'm looking at these values, the highest value I see on the y values is going to be a 1, and the lowest values I see for the y values is going to be a negative 1. And that's called the range of the function, but we'll look at that in a second. So it looks like the highest again is 1, so I'm going to come up here to a 1, and the lowest is a negative 1. And then I'm going to have some tick marks I can move along here. Now remember, these are my x values, these are the angles, these are the output or the y values. Now what I want to do is I want to plot these points, 0, pi over 6, pi over 2, but I want to be really consistent. So what I'm going to do is I'm only going to make tick marks at these important quadrantial points. So again, this is 0. I'm just going to kind of try and split this up evenly. Pi over 2 is my next quadrantial point. Pi, 3 pi over 2, and 2 pi. And I think I forgot pi in here. Pi would have gone right in between here. So the sine of pi is 0. We'll sneak that in. So as we plot these points, 0, 0. So the sine graph, if there's no transformations, and transformations would be things like multiplied by a 2 out front or a negative 6 inside, that type of thing, we would always start at the origin for the sine curve. Now the sine of pi over 2 we see is 1, so that would come up here. The sine of pi is back down at 0. The sine of 3 pi over 2 is a negative 1. And the sine of 2 pi is 0. Now if you connect these points you might think, oh, it's it's like a sharp V shape. But that's not really what's going on here. These are nice smooth curves. So to get in between what's happening here, pi over 2 is here. And if I just put in these smaller tick marks, here's pi over 6. Well, at pi over 6, I'm clear up here at 1/2 already. So you can see it's not a sharp point. It's starting to smooth this curve out. Now I can't put arrows on the end here and say this goes on forever in the positive direction. It stops and then it turns again. So I have to be careful. Arrows really are not appropriate for this curve because they do not go forever in the positive direction or forever in the negative direction. They stop at 1 and -1 vertically. So this is the easiest one, is to plot these quadrantial points. And don't forget this one that I forgot earlier. And this is the graph of my sine curve. Now I could have also extended it in this direction as well. Now there's some interesting characteristics that we see here. First of all, domain. And remember, domain are our x values. Domain is all real numbers. Meaning the domain horizontally, I can plug in any angle I want. So another way we could represent that is -infinity, less than x less than infinity, to represent the domain. Or we could do -infinity to infinity. Now we have parentheses, not brackets here, because I don't ever reach infinity, so it's really important that we don't have brackets. Brackets would mean I actually reach those points. Now range, okay, so domain was horizontal, left to right. Range is vertical, top to bottom. So for the range, I'm looking at y values. It's not all real numbers. The highest I go is 1, the lowest I go is -1. So this would look like -1 less than or equal to y less than or equal to 1. Okay, that means I can be between -1 and 1. I could equal -1 and I could equal 1. Another way I could write this is -1 bracket 1. I have brackets here because I actually reached those points -1 and 1. So there's some interesting characteristics of this graph. And remember, it moves forever in either direction following the same curve. So some interesting characteristics. This graph is continuous. Now when we talk about continuous, there's definitely a definition of continuity that you will learn in calculus. But for our purposes, could I trace this entire graph without lifting up my pencil? And the answer is yes. And if that's the case, it's continuous. And it's continuous over its entire domain. There's no holes, there's no gaps, there's no jumps. And again, that domain was negative to positive infinity. Now, x-intercepts. X-intercepts mean where they cross the x-axis. So my x-intercepts are at x equals 0, x equal pi, x equal 2 pi, and I bet you could guess the rest, 3 pi, 4 pi, 5 pi, -2 pi, -3 pi, etc. So the x-intercepts have a form of just n pi. And n in this case is some integer. It could be positive or negative. Okay, but it's a counting number, so I get those multiples of pi in the positive or the negative direction. Now when does it start to repeat itself? Well, when we get from 0 to 2 pi and I get to this point, when I start plugging in angles again, I'm going to start getting all the same xy values out. So it starts to repeat itself every 2 pi or every 1 spin around the unit circle. So its period is 2 pi. And basically this is how often it repeats itself. And you have to take a good look at a chunk of the graph to determine that. You can't just say, oh, it starts to repeat itself at pi because I hit that 0 again. Well, we can see that a little something happens different after that. So you have to make sure that you check a little bit beyond that. Now this has some other interesting characteristics. It's definitely symmetric. So it's symmetric with respect to the origin. Now it's hard to see this one specifically because I don't have much going on over here, but if it was symmetric with respect to the origin, basically I could draw this line and it would reflect across that. So this is symmetric with respect to the origin. So that means it's an odd function. Now odd not meaning weird or strange, odd just meaning it fits the definition of the sine of negative x is equal to the negative sine of x. Okay, that's its definition. So again, odd function. So that means if I take the sine of a negative number, let's say like -pi/2, what that's going to give me is a -1 down here at some point. And that's just equal to the sine of pi/2 negated. So that's the definition of our odd function there. Now one thing that we don't have here is our unit circle. So I want to go ahead and pop in our unit circle real quick. And so for our unit circle, I just want to look at what's going on with the y values, because sine is based on our y values. Okay, so again, sine are our y coordinates. So I'm not going to concern myself with the x values yet. So again, the x values, I just put in the letter x. Now this y just means output. It doesn't necessarily mean the cosine or the sine or anything to do with the trig functions. It just means our value. So if you wanted to, you wouldn't even really need to look at this as y equals sine x, but this is just the sine of x. This is the graph of the sine of x. Now when you look at some of your homework problems, as you start going through these, they will have the y equal, so I just want to make sure you're familiar with that. Well, if you notice, we're in quadrant 1 here. So here's quadrant 1, and in quadrant 1 I go from 0 degrees or 0 radians up to pi over 2 radians. So this bit right here, let's see if we can highlight that in. This bit right here, this is quadrant 1. This relates to quadrant 1. So my y values go from 0 to 1. So my y value here goes from 0 to 1. Now in quadrant 2, my y values are going from 1 back down to 0. So quadrant 2, we'll say, is right here. So this is Q2. Okay, and I'm just plotting those points for Q2. I guess I could move that up so it's a little easier to see. And so you can see what's happening here is this graph is being split into quarters. Okay, let's go ahead and look at Q3 next. Now for Q3, let's keep in mind I'm moving my y values from 0 to -1. So that's what's happening here, from 0 to -1. So that's Q3. And then my fourth quadrant, I'm moving from y values from -1 to 0. So if I look at those values from -1 to 0, let's see what's going to happen there. That's going to also be down in this region, and my y values move from -1 up to 0. So again, this was Q3, and this was Q4. Okay, so if you look at this, I have split this up into 4 pieces, 4 quadrants, and that's going to happen with your graphs all the time. I'll split them up into fourths, and in this particular case I take 0 to 2 pi, divide it by 4. 2 pi over 4 is pi over 2, and that's where I can come up with these nice little tick marks where I have my maximum and my crossing points for x-intercepts. So this is just a quick overview of the sine curve. Being able to graph the sine curve by hand is going to be really important. I also want to pull in graphing the sine curve on your calculator. So for graphing our sine curve, we go to y equal. We want to make sure you're in radian mode up here. If you're not in radian mode, make sure you go to radian mode under your mode key right here. And I want to graph the sine curve. I can use X, my shortcut key right here, close parenthesis, and this will just give me the graph of the sine of x. This kind of looks a lot different than what I have there. If you notice, I only go from -1 to 1, and I only go from 0 to 2 pi. So our values are different in terms of our maxes and our mins. So the way that we can change that is through the window. And through our window, I only had 0 to 2 pi. But let's say we want to go a little further. Now 2 times pi would be 2 times 3.14 is 6.28. So I want to go a little to the left and a little to the right. So I'm going to go -7 to 7. Now the x scale, I'm moving by 1 radian at a time, but remember those pi over 2 values are really handy. So I would like to go by pi over 2 tick marks. Now my y min and my y max, my y min was -1 and my y max was 1, but we want to go just a little beyond that just so we can see exactly what's going on. So I'm going to go 1.5 y min, it better be a negative 1.5 to a positive 1.5. And again, it's just so I can see a little bit better view of the graph, and I'm fine with the y equal 1 scale. Now this is a little more interesting. Now this is crossing where I'd expect. It's crossing at 0. I have this maximum point at pi over 2. Here's pi, 3 pi over 2, and 2 pi. So I don't see the tick marks here on the graph, but because I set the scale, I know what the tick marks are. Now another thing that you can do, if you want to figure out what this point is, you can go to second calc, and this would be a maximum point, so I could choose maximum. And I want to choose the maximum right up here, so I'd move my little flashy star to the left and to the right because it's asking me for the right bound, and hit enter. And it's saying y equal 1 is the high point, and it occurs at 1.5707977. That doesn't seem like an obvious point, but it's actually pi divided by 2, and you'll kind of get used to some of those decimal approximations with those ratios. So this is a nice little graph of the sine function. So let's go ahead and pop a screenshot of this into our information about the sine graph as well. And this is nice because it shows us more than one period. So it's going from here and it's repeating, so there's one period. There's 2 full periods showing here. So that's some interesting characteristics about the sine curve. The next thing we're going to be looking at is the cosine curve. Okay, so before we get to that, I'm going to make sure we write this out here, y equals sine of x. Now let's go ahead and look at cosine. So I'm writing this as a function, so y equal a function of x, y equal cosine of x. I'm going to graph this the same way. I'm going to choose some values for x, see what the values are for y. But I've learned something interesting here. Just the quadrantial points are actually helpful. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. Let's go ahead and put in that unit circle. I think we had a unit circle when we graphed the sine graph as well, to help us out with this. So if we look at the unit circle, I just want to look at the x values. So here we're at 0 radians, pi over 2, pi, 3 pi over 2, and 2 pi. I'll write this on the top. So I just want to know what my y value, or sorry, my x values are. So this is 1 and then some y value. This is 0 and some y value. Negative 1 and some y value. And this is 0 and some y value. So for 0, my cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is negative 1. Cosine of 3 pi over 2 is 0. And the cosine of 2 pi is 1. And then I start all over again. So the highest I go is 1. And the lowest I go is negative 1. Now if I did any transformations on the graph, for instance adding 4 or multiplying by 7 or having a negative 12 somewhere, it's going to change the location and perhaps even the general shape of the graph. But if I don't have any transformations, then I should just always be able to pick these quadrantial points, and then once I get to this 2 pi it will repeat itself. Okay, so let's go ahead and graph these points. I'm going to split this in quarters because I have 4 quadrants. So I'll have pi over 2, pi, 3 pi over 2, and 2 pi. So graphing, I'll graph and I'll be here at 0, 1. Okay, so that's different than the sine curve already, because remember the sine curve started at the origin. Pi over 2 is 0, pi is negative 1, 3 pi over 2 is 0, and 2 pi is 1. Now something I'd like you to keep in mind is this is not a sharp graph like a W or an M shape. This is a smooth curve, and so we need to make sure that we get the shape right. Now it's not a sharp line. It's also not a smooth curve that goes underneath somehow. It's a smooth curve that comes down. And we'll talk about concavity when you get to calculus, but there's concavity changes going on here. So that's kind of what this looks like. It looks like a flying bird just for this first period. So let's talk about some of the other characteristics of this graph. Let's see what we talked about for sine and make sure we get the same thing. So we talked about the quadrants, and we talked about the domain and the range, and then the other characteristics as well. So let's talk about the quadrants. So in terms of quadrants, this is the first quadrant because I go from 0 to pi over 2 on my x-axis. So this is quadrant 1. And in quadrant 1, that's going to match exactly what we have down here in this quadrant 1 in terms of I'm always having positive y values. I'm moving from 1 to 0, and you can see I'm moving from 1 down here to 0. So make sure you understand the relationship between the quadrants of the unit circle and the quarters, or the quadrants, of this graph as well. Okay, the next one we want to look at, let's look at quadrant 2. So here's quadrant 2. Quadrant 2, the graph falls below. So let's make sure we mark that. Quadrant 2. This is quadrant 1. So this is quadrant 2, quadrant 1. Okay, so let's see what happens next. I'm still below, and that would be in quadrant 3. So this is Q3. And if you notice, when I talk about quadrant 3, make sure I use Roman numerals there, my cosine values are all negative, so I'm all negative in this region. Next I have quadrant 4. Quadrant 4 is here. So this is Q4. And that's in this region. Now if you think about Q4, cosine is positive, and so all my cosine values up here are positive as well, and that's Q4. So make sure you understand the relationship between the unit circle and the curve, or the curve sketch of just the cosine function that we have going on here. Okay, let's talk about the domain. The domain is the same for sine as it is for cosine. Domain is horizontal. It's all real numbers. So I could talk about this in terms of negative infinity to x to infinity. No equal signs here, no brackets here because I never reach infinity. Now range is my vertical, up and down, not left to right. So it goes from -1 to 1. And I'll write our set builder notation first. Notice I have equal signs here because I actually reach -1 and 1. And I can also use brackets here. Okay, let's go ahead and talk about some of the other characteristics. This graph is also continuous over its entire domain. Okay, now that matches with the sine function for the domain, and it actually matches with the range as well, but the continuity is true for both too. So again, our just very easy look at the definition of continuity, I could graph this and trace it with my pencil and never pick up my pencil because there's no gaps, there's no jumps, there's no holes, and so it's continuous. Now for this one, the x-intercepts, meaning where I'm crossing the x-axis, I'm crossing at pi over 2, and then I'm crossing again at 3 pi over 2. Let's see if we could predict some of these. 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and I could have also moved in the negative direction, such as negative pi over 2, negative 3 pi over 2, etc. Well, last time we used integers like n pi, but that's not going to really work here because now I have odd multiples of pi over 2. So the way we write an odd number is we say 2n plus 1. Because if I double any number, I'd get an even number, and then if I add 1, I'll always get an odd number. And then I multiply that by pi over 2. So that's where I'll always find my x-intercepts for a cosine graph that has not been transformed. And when I talk about transformed, I mean like multiplying or dividing values or adding values to change anything. The period here is the same as it is for sine. It's 2 pi. It starts to repeat itself once we get down here to 2 pi. It turns back around. Now this one is also symmetric, but it's not symmetric with respect to the origin. This graph is symmetric with respect to the y-axis. Now if it's symmetric with respect to the y-axis, and we won't see it so much here, but basically it means it reflects from the right to the left. I could fold it over the y-axis and I would get a mirror image. And we'll see this a little bit better when we graph this on our calculators. Now if I have a graph that's symmetric with respect to the y-axis, we call this an even function. Now the characteristic that we want to know about for the even function is that the cosine of a negative value or a negative angle is equal to just the cosine of the positive of the angle. We get the same value back. Okay, and we'll be able to see this. For instance, if we chose pi over 2 won't work so well, but pi will. So if we look at pi, the cosine of pi is -1, and the cosine of negative pi is also equal to -1. So that's what that's saying. Let's go ahead and pull in our calculator. Let's do y equal, clear, and we want to do cosine of x. Now remember, make sure we're in radian mode, and the value for x I can use on this shortcut key. And let's go ahead and graph this. Now remember, I had everything set up from last time. My vertical was -1.5 to +1.5. My tick marks went by pi over 2. And I went from like -7 to 7 to make sure I was -2 pi to +2 pi and a little bit beyond. So x scale, this is pi over 2. So let's go ahead and hit that graph again. And this is the graph of the cosine function. And here we can really see that symmetry with respect to the y-axis. And we can also see the period. So symmetry with respect to the y-axis, if I folded this down the y-axis and I folded it, I'd have a mirror image on either side. So this is y equal cosine of x. Now you have to be careful when you graph. If you don't set up the scales correctly, you won't get these nice little cross points. You'll get them in between values that are default, that are selected by your calculator. So you have to make sure that you kind of control that. Now everything that we looked at so far, these have been just standard graphs. There's not anything going on here where you're changing anything, you're multiplying or dividing or changing anything like that. We want to start talking about some transformations of these, meaning what happens if I multiply by 2, what happens if I divide by 7, those types of things. But before that, I want to look at one more calculator bit. So if we look at the calculator, I want to show you some shortcut things here. I want to graph both of the cosine function and the sine function at the same time. So let's go and look at cosine and the sine. Now under our window here, you can say we have some very strange settings. We talked about going from x min to x max. That was like a -2 pi. So I could just put in 2 pi here and then put in a +2 pi. And it converts it for me, but a lot of times it's nice to go a little bit beyond that. I like those tick marks at pi over 2, so I can put in pi divided by 2 here. It doesn't keep them in fraction form. And then my y min and max, I could go with whatever I wanted. I think that I'll just go -2 to 2. I guess I could go -1 to 1, but it's gonna, you won't even hardly see the tick mark because it's going to come right up to it, and I'm going to go ahead and graph these. There's the cosine, there's the sine function. So cosine is in blue, sine is in red. It looks like if I just took this red graph and I picked it up and I scooted it to the left, pi over 2 units as it turns out, these graphs would be identical, and that's true. They're called sinusoidal graphs, meaning if I adjust one, if I just shift it, I will get the exact copy of the other graph. And that also has to do because they're cofunctions. So that idea of these graphs being cofunctions comes up again too. So another thing you can do if you're having troubles getting your graphs to be showing on your calculator, and again you need to be able to graph these by hand as well, but checking them on your calculator is a good idea. You could go to zoom, and there's a zoom trig here on number 7. And if you hit zoom trig, they kind of come up with their own standard screen, and this screen goes to I think like 11 pi over 4 to +11 pi over 4, and then -4 to +4. So it's a good way if you're graphing to kind of start with that as a quick graph to see, and then maybe adjust it if you need to. So again, the graphs of the sine and the cosine function. I don't like them to be squished so much, this -4 to 4, because I like to see more of the graph. I don't like all that white space. So I would prefer that, but the zoom trig option goes -4 to 4, and then we'll adjust if needed. So I'm going to pop this in there just because it's an interesting curve. Leave a little bit more room here. Okay, so the blue was the cosine graph, and the red is the sine graph. Okay, so now let's go ahead and start talking about transformations. The first type of transformation that we want to look at is an amplitude change. So for an amplitude change, let's go ahead and look at an example of a transform graph. Now, whether I use this for a sine graph or a cosine graph, it just doesn't matter. The amplitude effect will be the same. So let's go ahead and graph y equal, let's do 2 sine of x. And I'm going to be doing these by hand, and I'll also be doing them with our graphing calculator as well, so you can see the difference, but you need to know how to graph these by hand. So the only difference here is this 2 from what we've already graphed. So if I were to plot some points, and remember those quadrantial points were really helpful, pi over 2, pi, 3 pi over 2, 2 pi, and then it starts over again. And actually, this one I'm going to do it a little different. I'm going to start at -2 pi because we haven't graphed anything in the negative regions yet. So I want to make sure that you see something like that in case you come across it. So now I'm at pi over 2, pi, 3 pi over 2, and 2 pi. So if I were to graph, and let's graph the point x equals 0. The sine of 0 is 0. 0 times 2 is 0. Okay? Now that's going to be the same for 2 pi because it's the same point, and -2 pi because it's the same point. And if we think about negative pi, the sine of negative pi is 0. 0 times 2 is 0. Same for pi. So far this is not very interesting. I'm getting a lot of zeros. Let's look at -3 pi over 2. So the sine of -3 pi over 2, that's going to be the same as the sine of pi over 2, and the sine of pi over 2 is 1. So the sine of -3 pi over 2 is 1. The sine of negative pi over 2 is the same as 3 pi over 2, and that's a -1. So what I'm going to do is I'm going to graph these points. But you know what I did? I forgot to, these are all right, the 1, -1, 1, and -1, but I forgot to multiply them by 2. So this would be 1 times 2 is 2, -1 times 2 is -2, 1 times 2 is 2, 3 pi over 2 is -1 times 2 is -2. So I forgot to multiply that by out front. But I'm going to have to do this a little different because I want to go in the negative region too. Now remember, these are quadrantial points, so I want to split these both sides up into quarters. So the best way to do it is to split it in half and then half again. So this would be pi over 2, pi, 3 pi over 2, and 2 pi, negative pi over 2, negative pi, -3 pi over 2, and -2 pi. Okay, so if we plot these points at -2 pi, I'm at 0. Now I know my sine function, I always kind of draw these up real quick, my sine function should look something like that. Okay, so here I am at 0, at -3 pi over 2, I'm up here at 2. And at pi, negative pi, I'm at 0. At negative pi over 2, I'm at -2. And then at 0, I'm at 0. Pi over 2, I'm at 2. Pi, I'm at 0. 3 pi over 2, I'm at -2. And at 2 pi, I'm back at 0. Now again, this is not like an M or a W shape. This is a smooth curve. So I definitely have more than one period going on here. Now, how is this different than our sine graph? Well, our regular sine graph, just good old y equals sine of x without the 2, would have gone like this. I would have hit some of the same points, and some I wouldn't have. So it would have gone something like this. Okay, so you can see everything is the same here except this has been stretched. And it's been stretched by a factor of 2. So basically I took each of the y values that I had for my y equals sine x graph and I doubled it. I multiplied it by 2. So what I have here, this has been stretched. So the green graph, the 2 sine x graph, has been stretched by a factor of 2. So the amplitude changes. Now the amplitude used to be 1. The highest it got was 1. And now the amplitude will be 2. And for the amplitude, I just always take whatever is in front of the function that's being multiplied, and I take its absolute value. So whether this is your standard curve, and there's an implied 1 here, here the amplitude is 1. In the graph we just did, the amplitude is 2. So the way this ends up looking in general, and this would work for sine and cosine, if I have y equal a sine of x or y equal a cosine of x, a is the amplitude. Okay, and again, a cannot be equal to 0 here because if a was 0 I wouldn't have any graphs at all. So again, the amplitude is this value of a out front. And actually it's the absolute value of the a out front. And the reason it's a negative, if it's an absolute value, is if it was a negative 2, let's say, it ends up having another effect in flipping the graph, but the amplitude doesn't change. So this is an example of an amplitude change. And plotting points and knowing your unit circle is very, very important. So for this one, in the green graph, the domain has not changed, all real numbers. But the range has changed. The range has changed from -2 to 2. Okay, and again, that's the y equal 2 sine of x graph. The regular domain was just -1 to 1. So that's an example of an amplitude change. Now the next thing that we're going to look at is going to be a little bit different than an amplitude change, and then we'll also combine both of them. Oh, that's right, we're going to graph on our calculator too. So let's go ahead and graph on the calculator. Let's clear this off. So here, let's do y equals sine of x. So we'll have our standard curve first. And then on this one, I think we had an amplitude of 2, so let's do y equal 2 sine of x. So there is our blue graph, is our standard sine curve. The red graph, you can see, is the change in the amplitude is much higher. So you can see the differences in there for sure. So we'll paste this in. Now, what if a was a fraction? So this was an integer, but what if a was a fraction, let's say 2/3 or 4/5? Well, what would happen then, instead of stretching, it would compress. So if a is a fraction less than 1, this would compress. So again, our blue graph is just sine of x. Our red graph is 2 sine of x. So we can see it still has all the same crossing points, all the same x-intercepts, so I haven't really changed anything here. Now that is a vertical stretch. I can also have a vertical compression, or a smushing if you want to think about it like that, is if my value of a is a fraction less than 1. The next thing I want to do is I want to look at horizontal stretch and compression. Now this does not necessarily have anything to do with amplitude, but at some point we'll combine all of these. So this either has to do with stretching out or squishing together, stretch or compression. So when we talk about horizontal stretch or compression, it's usually easier to think about this in terms of quadrants to see what the quadrants are doing. So last time we talked about the sine curve. For this example, let's talk about the cosine curve. So let's go ahead and look at y equal cosine, and let's say 4x. Now notice for amplitude, it was on the outside of the function. For horizontal stretch or compression, it's on the inside of the function. So that's kind of an interesting effect. So what this does, it affects the horizontal stretch or compression. So what I do to figure out what's going on here is I take the period and divide it by this coefficient, and the coefficient that we'll call this is b. And I'll show you what this looks like in general. So y equal cosine of bx, y equals the sine of bx. So whatever this coefficient is in front of the variable then would be my value of b. So for our example, the period for cosine we have memorized to be 2 pi. 2 pi over 4 reduces to pi over 2. So the period of y equal cosine of 4x is pi over 2. Now remember those nice quadrantial points we had before? I would get -1 and 1. I'd get those nice values to graph. I can do the same thing here, but I'm going to have to split these up a little bit differently. So I take the period 2 pi over b in this case, or 2 pi over 4, and I look at the interval 0 to pi over 2, because that's going to be an entire graph. So my cosine curve looks like this. Okay, starts up at 1, not at the origin. And it's going to start up again from 0 to pi over 2 right here. So I need to find those quarter points at where they're splitting up. So in order to do that easily, what we can do is we can take pi over 2 and multiply it by a fourth, because I want to see what's going to split these up as. And because again, these are quarter points, so this is pi over 8. So this particular problem, I'm going to start at 0, just like I always would. So I'm going to have 0 pi over 8. Pi over 8 plus pi over 8 is 2 pi over 8. Plus pi over 8 is 3 pi over 8. Plus pi over 8 is 4 pi over 8. So these are my quarter points, if you want to think about it like that. And of course, if you reduced them, pi over 8, this reduces to pi over 4, 3 pi over 8, pi over 2. So these are my important points of interest. So now when I create that table, like we usually do, plugging in numbers or angles, let's say like pi, etc., pi over 2, 3 pi over 2, they might not really create these nice values that I'm looking for. So I'm going to put in 0, pi over 8, pi over 4, 3 pi over 8, and pi over 2. Let's see what happens here. So if I plug in a 0, the cosine is 0. 4 times 0 is 0. Cosine of 0 is 1. Let's plug in a pi over 8. 4 pi over 8 is the same as pi over 2. The cosine of pi over 2 is 0. So again, you have to know your unit circle. Pi over 4, the 4's cancel. Cosine of pi is -1. 3 pi over 8 would reduce to 3 pi over 4. I'm sorry, 3 pi over 2. Cosine of 3 pi over 2 is 0. If I plug in a pi over 2, I am left with 2 pi, and the cosine of 2 pi is 1. So these are my nice quadrantial points. Now if you notice, the highest we go is 1, the lowest we go is -1. So there's no vertical stretch or compression here. It's all horizontal. We're about to see that. So I'm still going to quarter these, but instead of going by pi over 2s, now I'm going by pi over 8. So this is pi over 8, 2 pi over 8, which is pi over 4, 3 pi over 8, and 4 pi over 8, which is pi over 2. I still have these points though at 1. It still has the same cross points. It's looking the same. The only thing that really has changed here is the scale. Okay, and again, this would come around and continue that same pattern. So this would be my graph. Now if I had to graph my other graph with this, it would be like 4 times this wide. So this has been a big compression. Now the other one was a stretch when I multiplied by 2, but because this is inside the argument, it ends up being a compression because I'm dividing by 4. So here the effect is opposite. We're dividing by 4, so it's a compression. So these are called quarter points, if you want to think about it like this. So this is the left endpoint. This would be the first quarter point. This would be the second quarter point, third quarter point, and this would be the right endpoint. So if you get handy at creating these endpoints, they're going to really be nice. They'll be very helpful to you. Let's go ahead and graph this so we can use that as well. So let's start with just our standard cosine graph. And then we did cosine of 4x. Okay, so there's our cosine graph in the blue, and then you can see in this red, look at how compressed that is. Okay, so it's going from 0 to pi over 2. Let's look at our window here. So if we look at our window, this is going by pi over 2 units. Pi over 2 units, we really should have gone by pi over 8 units for our red graph, but it works well for our original graph. So we can keep it like that if we want, or we could switch it. But this is an example of how that works. I kind of want to change that. Let's change that to x scale to pi over 8, because that was our new quarter points when we took our period pi over 2 and divided it by 4. So now we can see the cross points. The general shape is the same, but we can see the cross points a lot easier. So it's kind of hard to see here, but this was definitely a compression. So our blue graph is equal to cosine of x, and our red graph is equal to the cosine of 4x. So this has definitely been a compression. I took that graph that was all spread out and I compressed it into a much smaller region. Now we haven't got a lot of time to go through a lot of problems, because you can see that one problem takes quite a while. But the more you practice these, the better you're going to get at them. The graphing calculator is very, very helpful, but a couple things I want you to keep in mind is you need to be able to do these by hand. And in so saying that, let's go ahead and come up with a strategy for graphing these. And I think the best way to come up with a strategy is to look at an example. So let's go ahead and look at the graph. We did a sine and a cosine, so let's go ahead and go back to sine. Y equal negative 2 sine 3x. There's a lot going on here. There's 3 transformations. So the first transformation is this negative sign. Now the negative, we haven't talked about this, but we'll see it in this example. This is a reflection. Okay, and we'll see how that reflects, but it's a reflection over the x-axis. So that's our first transformation. The second transformation is the 2. This is a vertical stretch by a factor of 2. And then this 3. Okay, so this 3, I know it's a horizontal because it's inside the argument. Now it seems like it should be a stretch because 2 was a stretch, so 3 should be a stretch as well. But this is a compression because it does the opposite. So this is a horizontal compression by a factor of 1/3. Now the reason we say 1/3 is I take 1 over the 3. So I have a lot of things going on here. So let's come up with our strategy. So step 1. And again, you'll be expected to graph these by hand. Checking with your calculator is great, but you're going to have to find these cross points and quarter points and left and right endpoints by hand, so make sure you follow along with that. So step 1, find the period. Now the period for the standard sine curve is 2 pi. So we would take the period of 2 pi and we divide it by this value of 3. So 2 pi over 3 is the new period. Now remember, we like these quarter points, and so we're going to take quarter points. So these are our quarter points. So what I can do here then is to divide these up into 4 even parts. I would take 2 pi over 3 times a quarter. Okay, this would give me 2 pi over 12, which is pi over 6. So this is the width of each quarter. So usually with my cosine graph, I'd start at 0, and I'm going to add a pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. So if you notice, I have 1, 2, 3, 4 quarters, which is what we want. Now we're going to rewrite these in reduced form. So they're going to be 0, pi over 6, pi over 3, because 2 pi over 6 reduces, pi over 2, and 2 pi over 3. So this is my left endpoint. This is my first quarter point, second quarter point, third quarter point, and this is my right endpoint. So if we follow this process, we'll always be able to get to the correct graph because it takes us through kind of a step-by-step process. Now what we want to do is we want to evaluate the function at these points. So step 3, evaluate the function at the points in step 2. These quarter points, right endpoint and left endpoint. So let's go ahead and create a chart. So a nice way to kind of organize this, last time we did vertical, but we're getting too much information here. So let's go ahead and look at our x values first that we're going to plug in. And I'm going to write them across this time. I'm going to go 0, pi over 6, pi over 3, pi over 2, 2 pi over 3. Now this is just a systematic way of helping us evaluate these. Because when I was doing these last time, I was like, okay, you plug in a 2, 2 times pi over 2 is pi, sine of pi. So we went through that, but let's go ahead and write this out. So here's x. Now remember, my graph was sine of 3x. So let's figure out what 3x would be. So I'd multiply each of these times 3. 3 pi over 6 would be pi over 2. 3 pi over 3 would be pi. 3 times pi over 2 is 3 pi over 2. And 3 times 2 pi over 3 would be 2 pi. So there's 3x. Now I want to know what the sine of 3x is. So what's the sine of 0? It's 0. The sine of pi over 2 is 1. The sine of pi is 0. The sine of 3 pi over 2 is -1. And the sine of 2 pi is 0. So see how nicely this helps us keep track of that. Now next we need it to have a -2 times the sine of 3x. So what we do is we just take -2 times what we have here in this row. So -2 times 0 is 0, -2 times 1 is -2, -2 times 0 is 0, -2 times -1 is 2, -2 times 0 is 0. So those are my nice points. Those are my plot points. So step 3, we're going to evaluate the function. Step 4, we're going to actually plot the points. So we want to keep this on the screen. So step 4, plot the points from step 3. Okay, so I'm going to be plotting the point 0, 0. So the points that are important are this one for my x value, and this is really my y value. Now I could just kind of focus on that first quadrant, but I might want to expand this in the negative direction too, so I'm going to leave a little extra space. Now the highest I go and the lowest I go, 1, 2, 3, is -2 and +2. Now again, I want to take these and split them up into quarters. So I split them in half twice. And my important points here are pi over 6, pi over 3, pi over 2, and 2 pi over 3. So pi over 6, pi over 3, pi over 2, and 2 pi over 3. And I could have -pi over 6, -pi over 3, -pi over 2, -2 pi over 3. So here I am at 2 pi over 3, which is the same as 4 pi over 6, plus a pi over 6 would be 5 pi over 6, 6 pi over 6, which is just pi, 7 pi over 6, 8 pi over 6, which would be 4 pi over 3. So I could find these values as well. I'm just going to plot one period from those points, and then I'm going to work from there to expand it, because I know it repeats. So I start at 0. If I plug a 0 in, I get a 0 back out. That's from this point and this point. Next, pi over 6, negative 2. So pi over 6, negative 2. Pi over 3 is 0. Pi over 2 is 2. And 2 pi over 3 is 0. So there's one full period of my sine curve. Now this looks very different than the sine curve before. So remember, the sine curve before started and went up. So the regular sine curve would go like this. Now this is negated, so what ends up happening is I still start at the origin, but I go down. Okay, so that's the difference. That's the effect of that negative reflection across the x-axis. So there's what I graphed. Now from here, what I could do is I could just continue on with this pattern. Okay, and if I continue on with this pattern, here's the second period of my sine graph that I have plotted, negative 2 sine 3x, I believe it was. Here's another period. So if we move up here, so I have 3 full periods here that are shown. So that would be an example of drawing the graph then and sketching those additional periods. So that's step 4. Step 5 is technically connecting the points. So this is an overview. If you follow the steps, you'll be fine. We should graph this one with our calculator just to compare. I know this lecture is getting long, but I wanted to make sure you got to see one good example of combining these. Let's look at negative 2 sine 3x. So let's graph that one. So that should match what we have, and it very well could. It's kind of hard to tell with all the changes. So let's go back up here and just graph the sine graph. And again, it's hard to distinguish these sometimes, but this is the original graph versus the transform graph. And you should be able to graph both of these by hand. And when you learn to graph these by hand, you learn a lot more than if you're just graphing and having the calculator do the work for you, because you don't understand like the quarter points, the x-intercepts, etc. So our blue graph is equal to the sine of x. Our red graph is equal to negative 2 sine of 3x. Okay, so as usual, if you have questions, let me know. And I know I've said this several times in the video, but please make sure you know how to do these by hand and not just with your calculators. Questions, send me a screenshot and I'm happy to help out. Thank you.